everybody. I just wanted to add a little addendum to our discussion of Lagrange's theorem, and that is a counterexample to the statement that would be the converse of the theorem. In other words, I want to show that just because you have a divisor of the order of a group, it doesn't mean there's a subgroup with that many elements. And the example I want to look at, I've taken from the book, and it's the group A4. So remember what A4 is. A4 is the collection of permutations in the symmetric group with 4 elements such that G is an even permutation. And even permutations of 4 elements are either the identity element, or they're of the form a product of transpositions like this, or they're a 3-cycle. Because in S4, you have also the transpositions, just like 1, 2, but that's an odd permutation because it's the product of 1 transposition. And you also have the 4 cycles, but the 4 cycles are also odd. Remember that a cycle is odd if it's, an odd cycle is even and an even cycle is odd. So the elements of A4 consist of products of transpositions, the identity element, and 3 cycles. And there are really 3 of these products of transpositions. They look like that, depending on how you group the 4 elements. Okay, so now we're going to prove that H has no subgroup of order 6. So we're going to do this by contradiction. So suppose that it does have a subgroup of order 6. And let's try to figure out what the elements are in H. So the first thing I want to point out is that there are a total of 8 3 cycles in the group A4. And why is that true? Well, how do you make a 3 cycle? To make a 3 cycle, you first pick 3 of the 4 elements, 1, 2, 3, 4, and there are 4 choose 3 or 4 ways to do that. So just for instance, these are just the subgroups like 1, 2, 3, 1, 2, 4, 1, 3, 4, and 2, 3, 4. And then each of those sets gives rise to 2 3 cycles. So for instance, if you take 1, 2, 3, you can do the permutation which sends 1 to 2, 2 to 3, and 3 to 1. Or you can do the permutation which sends 1 to 3, 3 to 2, and 1 to 3, 3 to 2, and 2 to 1. And these permutations are inverse to one another. If you were looking at the triangle, they would be left and right rotations of the equilateral triangle. So each of these sets of 3 elements gives rise to 2 permutations. And so there's a total here of 4 times 2 is 8 3 cycles. And they come in pairs, G and G inverse. Okay, well now we have our subgroup H. It has 6 elements. Here's H. And because of Lagrange's theorem, we know that the index of H in G is 2. That means there are 2 cosets. So one of them is the coset H and the other is the other coset, GH, and it also has 6 elements. And now we have 8 3 cycles. So it's clear that however we arrange the 3 cycles, at least 2 3 cycles must be in H. Because even if we stick 6 3 cycles into the other coset, we're still left with 2 that have to go into H. And H is a subgroup. Well, so let's start there. So, and H is a subgroup. So if you put a 3 cycle into H, you also have to put the inverse of that 3 cycle into H, because subgroups have to contain their elements and their inverses. So remember that the 3 cycles come in pairs of their inverses, and at least one of those pairs has to be in H. So let's assume, just for simplicity, that 1, 2, 3, and 1, 3, 2 are in H. So now we've accounted for 3 elements of H. We know about the identity element, we know about 1, 3, 2, and we know about 1, 2, 3, and there's space for 3 more elements in H. So what could those 3 elements be? Well, one possibility is that we could put another 3 cycle into H. But if we put another 3 cycle into H, then we also have to put the inverse of that 3 cycle into H. So let's see what happens if we do that. So suppose the next 3 cycle that we put in is 1, 2, 4. Any other 3 cycle, if you look at 1, 2, 3, the other 3 cycles are gotten by either changing the 1 to 4, the 2 to 4, or the 3 to 4. So they're going to have 2 things in common plus a 4, so it doesn't really matter which example we pick. So suppose 1, 2, 4 belongs to H. Well, again, it comes with its inverse. If 1, 2, 4 is in H, then its inverse 1, 4, 2 has to also be in H. But if 1, 2, 4 is in H and 1, 2, 3 is in H, then the product of those 2 things has to be in H. And if we multiply 1, 2, 3 times 1, 2, 4, so we have 1 goes to 2, goes to 3. So we have 1 goes to 3, and then 3 goes to 1. So that's where this transposition comes from. And then we have 2 goes to 4, and then 4 goes to 1 goes to 2, and that's where this comes. So if we have 1, 2, 3, and 1, 2, 4, then we also have to have the product of transpositions 1, 3, 2, 4. And that's 6 elements: an identity, 4 3 cycles, and this 1, 3, 2, 4. And so we might think, okay, we're happy. But not so fast. If you have 1, 2, 3, and 1, 2, 4, you also have to have 1, 2, 4 times 1, 2, 3. I mean, both products have to belong to the group. And if you multiply 1, 2, 4 times 1, 2, 3, let's see, 2 goes to 3, and then 3 goes to 1 goes to 2, and then 1 goes to 2, and 2 goes to 4, and finally 4 goes to 1. So the product in the other order is also a product of transpositions, but it's a different product of transpositions. And that also has to be in H. So now we have a problem. We have 7 elements in H, and that's a problem because we were trying to make one with 6. So, okay, so remember how we got to that situation. We assumed that there was another 3 cycle in H. So suppose that's not the case. So our H consists of the identity element, 2 3 cycles, and the remaining 3 elements in the group, which are the products of transpositions, 1, 3, 2, 4, 1, 4, 2, 3, and 1, 2, 3, 4. So that seems like it would be okay, except that if we have, so our picture here is that H looks like the identity, 1, 3, 2, 1, 2, 3, and then also 1, 3, 2, 4, 1, 4, 2, 3, and 1, 2, 3, 4. And that's 6 elements, and we think, okay, great. But the subgroup has to be closed under multiplication. And if we take 1, 2, 3, and we multiply it times 1, 2, 3, 4, well, let's see what happens. 1 goes to 2 goes to 3. So 1 goes to 3. 3 goes to 4. And then 4 goes to 3 goes to 1. So the product of those permutations is the 3 cycle 3, 4, 1. And that also has to be in H. And again, we've got 7 elements in H, and it was supposed to only have 6. And so again, we have a contradiction. And we've seen that there's simply no way to pack together 6 elements and still make it a subgroup inside A4. Or put another way, if you have 6 elements in H, you automatically have all 12. There's just no other way to arrange it. So that's a little argument that shows why the converse of Lagrange's theorem can't be true, even in this simple case.